So now we go back to our structured data and let's see some of the machine learning, the popular or traditional machine learning tasks on such data. Let's start with graphs. Okay, so in general, the kind of functions we learned on graphs have the form of, take as input a graph and a node or a sequence of nodes, and you produce a number or a sequence of numbers. Okay, and sometimes the graphs will be featured, and then we require all graphs in this class to be of the same feature dimension. And in the case of heterogeneous graphs, we require the graphs to be type consistent. Okay, so let's see the examples. So the first is node classification. And an example is that each node, say, represents a student, and we want to predict whether the student is going to graduate within 4 years of studies. Okay, so so this is binary classification. We can also look at the multi-class classification. There is also the corresponding task of node regression. For example, you want to predict the average grade or the number of points of the student by the end of the year. Node embedding. So an example of that would be the following. Suppose that your graph represents a protein. So every node represents an amino acid, and we want to predict a relative point in 3 dimensions. Why so? Because we want to predict the folding, the shape of the protein in a folded state. So we basically want to predict the position of every node amino acid in this folding, in this shape. Okay, and this is also a task that we will see throughout the course as playing a part in link prediction. Another task is node clustering. Okay, where basically we want to partition the nodes into clusters. We want to associate every node with an integer such that two nodes belong to the same cluster if and only if they have the same value. We predict the same cluster number for them. Okay, so this is known as a community detection. Now, beyond nodes, we have tasks like link prediction. Okay, so for example, some nodes represent students and some nodes represent courses, and we want to predict which student is going to take which course, or have product nodes and customer nodes, and we want to know which customer buys which product or will buy which product. Okay, and there are tasks at the level of the graph. Okay, for example, we want to classify a graph based on some property or predict a number for the graph. For example, if a graph represents a molecule, then we want to determine, predict whether it is toxic. Okay, or we want to guess its level of toxicity. And you can think of things like similarity embedding. You want to embed the full graph, the full molecule, say, so that similar molecules or molecules that behave the same are mapped to nearby vectors. That's a classic task of embedding. Okay, and you can think of variations of these tasks. What about tables? So we have a table following again the tabular signature, a sequence of attributes and a domain. And you can think of tasks like classifying every tuple, okay, or a row regression, row classification, where basically we want to learn a function that maps every possible tuple to value. Again, in general, it can be a sequence of numbers. Column prediction is basically the special case where you want to classify the road into one value or predict one value of the road. So another way of looking at it is that you have a table R with a column AI, which is missing, and you want to complete this missing column. Okay, and it can be Boolean, binary classification, or categorical, and then it will be, say, multi-class classification. Numerical will give you regression. There's a problem of data imputation, missing data imputation, where basically you're given a database R prime, but several cells are missing, and you want to guess what are the missing values. Or data cleaning. You get a complete table R prime, but it has some errors in the cell. Some values are erroneous, and you want to guess which cells have the wrong values and what is the correction of them. Usually, or in many cases, this is kind of the same task. Entity resolution. You get a table and you want to know which rows refer to the same real world entity. So it's kind of a clustering problem, but it has like a specific meaning, specific semantics. It also goes by the name of deduplication, and actually there are many, many names for this task. Now let's go to relational databases. Now we have schema, okay, with the foreign keys and the signatures of the relations and so on, where relation names are, and we denote here by DS, the set of the all databases over the schema S. And so basically every task that is defined on tables is also defined, similarly on relational databases where you take one of the tables and apply this prediction to it. But now you have information, you have access to all of the database, not just the row, but say also the tuples that connect to this row and the tuples that connect to the tuples of this row. So we have more information, but the task is the same, okay? Something that is special to our case is entity linking or entity matching, where you get two relations, R and S, and you want to learn which R tuples are connected to which S tuples. So, for example, R can be the customer rows and or customer relation, and the S can be the product relation. And you want to know which customer rows will purchase, within the next month, which product rows. Okay. Forecasting, relational forecasting. So this is a more, open-ended general problem. But you can generally define it as follows. So you have a database that changes over time. New tuples come in, new tuples, the old tuples are deleted, and so on. So DT represents the database at time T. Now you also have a numerical query, say the number of purchases over a month, or the total number of purchases in the database. And you want to predict the answer to this query over dt, but at a future time t. Okay, so here I give the example of October 2026 sales of customers from Berlin. And the time of the sales can be from one table, and you have the customers in another table and their addresses in yet another table. Okay. I will say something about invariance of models. We're going to see it later in the course, but this is an important aspect. The models that we learn over the structured data should have some properties of invariance, or typically we want them to have some properties of invariance, which means that they are essentially resilient to changes, variations of the data that we consider, unimportant. For example, if you have a database or a table, you want to say in many cases, well, the order of the columns doesn't matter, or the order of the tuples doesn't matter, or if we use some opaque keys and replace them with something else, that shouldn't matter. What do we mean by shouldn't matter? These changes should not affect the quality of your prediction. It doesn't make sense that you make such changes and suddenly the quality of your prediction drops dramatically. Why? Because we consider these as operations that do not really change the semantics of the data. In certain situations, when one may want to say, well, I want a model that is invariant to the attribute names. Okay, but that depends on the task. In some tasks, the attribute name actually can matter. The point is that we need these models to feature these invariants, but of course, it doesn't mean that if we take a database and reorder the columns or do some standard redesign, then the model continues to work. It might break. Okay, it expected to see a text in some column and suddenly, or in the second column, and suddenly it sees a number. Okay, uh, so the point is we want invariance, but we should be careful in how we define invariance. We'll see that during the course. Now, there is a class of machine learning tasks that I'm not going to discuss in the course, but it's important for me to mention these. You're aware of them, make you aware of them, and know that we're not going to discuss them. And these are the schema level tasks. And these are predictions that essentially predicts things at the level of the database schema, the meta level. Okay, for example, schema matching. You're given two schemas, S and S prime, and they represent, say, similar domains, and you want to know which pairs of attributes, one from S, one from S prime, represent the same entity type, the same information. Okay, the person's name in one place and I don't know, last name in another place, or the company's location versus company facility. Query learning. Query learning is the task that is defined as follows. I give you a database and query answers, and I want you to guess what the query is. Okay, like what is the SQL query that produces this result? And there can be many SQL queries. So there is also the um, human aspect of it. You want to predict which query a human would write to produce these answers. This is a very interesting problem. Text to SQL. You have a schema S and you have a textual description, and you want to have a query that works on this, compiles on this, and gives you is actually the correct description or correct representation of the textual description. And this is a task that nowadays LLMs solve very effectively. Okay, but again, schema level tasks are not covered in the course. That's all.